Hello everyone, I'm Vishwesh Trivedi, a graduate student at NYU pursuing computer science. And today we're going to discuss this paper called Closing the Curious Case of Neural Text Degeneration. This paper was submitted to ICLR this year, actually last year, 2024. So we'll see what this paper is about. The agenda is going to be in these five sections. So let's get started. The paper presents a theoretical proof to explain the effectiveness of threshold based truncation sampling. Now, it is fine if you don't know what truncation sampling is, we're going to discuss that. But basically, this paper provides a theoretical proof on uh, explaining how it actually works behind the scenes. It also presents a new strategy called basis aware threshold sampling or BAT sampling that, unlike pure threshold based truncation sampling, does not rely solely on a numeric threshold. So, we will discuss what this new strategy is about, what was the motivation, etc. And lastly, the authors show theoretically and empirically how the proposed method can selectively discard low quality tokens while still keeping high quality but low probability tokens, thereby being closer to the true token distribution. So all of this we're going to discuss later. So let's get some background. The first thing that we need to know is decoding strategies. Now, a lot of the audience might already know what a decoding strategy is, but just to brush it over, all LLMs, as we know currently, whether we talk about GPT-2 or some of the other LLMs, they are autoregressive. That means they produce one token at a time, and this token is fed back into the model to produce the next token. So now the question is, when so here on the right I have the transform architecture, the classic architecture. GPT just has this decoder, decoding block, but in this case, let's say it's an encoder decoder architecture. Then here what we have at the end is a probability distribution over all the tokens in the vocabulary, through which we sample the token that is considered the next token. So when the model has this sentence called deep learning, the next token is actually one of the all the v tokens in the probability distribution, and we just sample this token is auto regressively to get the next sentences, get the next tokens over time. So the idea is that either we can take the most probable token, or we can consider any other sampling strategy which does not take the most probable token. So a very good comprehensive guide is the one that I attach here in the link. It's the good median blog on decoding algorithms. So let's actually go through what a decoding algorithm is. So this is an example of the softmax that comes at the end of the transformer block here. Now, here there are several strategies. The easiest one, as you can guess, is just take the most probable token at every step. Now, the problems with this is there are a lot of instances where the model actually has repetitive answers after some point. Because if you think about it, what we are trying to do is we're trying to condition a model that whenever you come across a certain prefix of tokens, you have to output one specific token deterministically. So let's say a lot of the sentences in my like in my training set have I like playing football, I like playing football. So whenever it has I like playing as a prefix, there is no other token that will output other than football. So this might lead to a lot of repetition, which we do not really want. Second is ancestral sampling. Now, this is actually a fancy word for beam search. So, a beam search is basically instead of just taking the top token, you actually consider all the tokens by the proportion of probabilities. So, in my case, if my first token has 30% probability, and in the decreasing order it has 20, 10, 5, 4, 3, and in a certain decreasing order, then I basically sample based on those probabilities. Now the problem is here, uh, the LLM actually, we'll see how, but the LLM actually estimates the true probability distribution rather than actually giving the true probability distribution. So instead of having the actual tokens, we have a long tail of very improbable tokens that the LLM can sample from. So assume that 90% of the tokens are actually useful, but the rest 10% of the tokens are will never occur in a real sentence, but still the LLM has a 10% chance of sampling from those tokens. So that is a big problem. Again, also you cannot sample through the entire vocabulary, because vocabulary nowadays is upwards of, let's say, 40,000 or 50,000 words. So it is a computational bottleneck, and it does not really give, it sometimes gives a very random word in the middle of the sentence. Hence, this invited a lot of threshold based sampling techniques. So, I'll discuss a few which we might need in the future. But just going back to the blog that I mentioned, that is a great blog for anyone who wants to actually go into coding up any of these strategies and looking for themselves. So here I'm showing a visualization for the two very famous strategies. It's called top k sampling and nucleus p sampling. The idea is very simple. In the first one, the top k sampling, what we do is we only sample the top k tokens at every step, and this k is a fixed heuristic. uh, Obviously this k might also, you can have a design choice where this k might change over time, or there can be some scheduler for k, but let's, for simplicity, let's assume this k is fixed. So let at every point you just sample k tokens, and then on those k tokens you normalize it to their probabilities. You normalize the probabilities over those k tokens to sample one particular token at a time. Because remember, we can only take one token at a time, but our pool, the pool that we sample from is what we are trying to decide here. So let's say in this example, if I had 90% of the tokens, 90% of the tokens, like 90% of the probability in the top k, then this means that my probability will be normalized over the 90%. So if a token had zero point 0.4 probability out of the 90%, then it will become zero point 0.4 into 10 by 9. That is its new probability of sampling. Similarly, nucleus sampling is one of the most popular methods right now. And instead of having the difference between nucleus sampling and top k is that top k has a fixed number of tokens that it samples from, and nucleus sampling actually does not fix the number of tokens, but rather it fixes a threshold of probability that should add up when I'm sampling from a pool. So here, as you can see, my k is fixed. I guess it is up to, I think, 20. So only 20 tokens are sampled regardless of the distribution of the tokens. But here top p sampling actually takes into account the distribution of the tokens and sees that, okay, if there is a spike in the distribution, that means there are only few probable words, then the top p will actually close out very early. And if there is a relatively smoother distribution, then the top p might extend, like then the number of tokens I sample from might be larger. So hence my threshold actually moves depending on my distribution. So these are some threshold sampling strategies. Now we need to actually, so I mentioned that we actually don't really estimate the true probability distribution, and rather, like, we rather estimate the probability. Now why is that the case? Like, if I have an infinite potential model, then why cannot I really just why do I have to approximate like the token probability distribution for my training samples? So here brings us to the main problem, that basically the main problem that the paper kind of regresses upon. It basically mentions this problem and shows how threshold sampling actually solves it. So the problem here is as follows. We have this thing called the softmax bottleneck. This refers to the limited expressivity of models with a small hidden size and a large vocabulary. So just to go over what is a hidden size, what is vocabulary. I mean, a lot of the audience already know this, but just by the fear of being redundant, uh, the hidden size is the dimension of my token. So in case of, let's say, GPT-4, I have 768 hidden dimension size, and the v, or the vocabulary, is the size of my vocabulary. This goes actually upwards of 40, 50,000, or even 100,000 for some of these models. So there is a stark disparity between the size of the hidden size, which is actually in order of 10 to power 3, compared to my vocabulary, which is in orders upwards of 10 to power 5 or 6. So why does this cause a problem? Because when we actually, so assume our true token distribution is basically just a log of all the basically here log p star means p star is my true probability of a token appearing, token I appearing if there is a prefix j. So given a prefix j, what is the true probability of a token I appearing? And that is my aij in the matrix. Now I want to estimate the a matrix. So what I do is I actually take my weight, which is of dimension v cross d. So the weight here is basically the embedding matrix w, because here I have d dimensions and I want to project it into v dimensions. So I have a v cross d matrix. Then I have a hidden state which is of d cross n, and here d basically is my hidden size and n is my number of samples. my number of tokens. So I'm assuming that I have a very long context length which is even bigger than v. So the minimum of v comma n is v. This is my assumption here. So the rank of the original matrix is v, that is that has to be parked somewhere. So in our case, v cross d and d cross n is my wh matrix, and then I subtract basically the diagonal j, which is like I'm trying to take the exponent of wh and do a log summation, a log sum over it. So this basically gives me, like, this basically is a like a spread out version of the softmax function. Softmax is basically I uh, I take a token of distribution and then I normalize it such that the sum of all the probabilities is 1 and all the probabilities are greater than 0. So here, instead of having a v rank, I actually have a d plus 1 rank, because even though my matrix w into h is of size v cross n, which I will assume naturally that will have rank v, but because it has a smaller bottleneck d, and hence its rank is actually minimum of v comma d comma n, which is d. And using a rank sum rule, actually I have the dimension as d plus 1, because if I have a matrix of rank a and I sum it up with a matrix of rank b, my information actually increases, so it's the rank is actually a plus b. So my rank is d plus 1 compared to my original rank, which is v. So there is so if v is bigger than d, v is greater than d, then a dash can at best be a low rank approximation of a. So this is the underlying problem. Now, how do we solve this? Like, what do we infer from this? So now, from this equation, from this theorem, from this EYM theorem for low rank approximations, what we see is that the uh, difference in the Frobenius norm. So just to not trying to delve into all of these mathematical terms, I've just written that it is kind of a Euclidean L2 norm, basically a square root norm of a matrix. So L2 norm is usually defined for vectors. So Frobenius norm is very analogous to a L2 norm for a matrix. Now, my difference, basically the distance between these two matrices, to be very vague about it, is actually proportional to the difference between v and d. This is what this equation is trying to say. Let's infer how. So here this equation says that the Frobenius norm between a and a dash is the summation over all the singular values of a. Now singular values again is can be thought of as eigenvalues for non-square matrices, because we don't actually define eigenvalues for non-square matrices. Singular values is like a extension of eigenvalues for non-square matrices. Now assume that my a is actually a normal distribution, then my singular values will more or less be constant over time. They'll be same, and hence the major factor here is actually v minus d plus 2, if you see here. So the difference, the more number of terms I add on the right hand side, basically the difference between v and d will actually increase the amount of error I have in estimating the probability distributions. Here on the right, I have just given a simple visualization where what might be happening, that there is a true distribution and there is an estimated distribution, and for some tokens I'm actually overestimating their actual probabilities, while for some tokens I'm underestimating. That's a simple, like, that's a simple extrapolation of what an error is. So this is what's happening. I'm not able to actually determine the true distribution of tokens, but rather I'm estimating it due to using a low rank approximation of a. So, to know more about EYM theorem, it's a lot of math. If you would like to know it, I've given a link here. You can click and you can go around. So, after covering enough background, I think we know what a softmax bottleneck is. So, let's go through what is a theoretical explanation of truncation sampling. So, truncation sampling refers to this process of drawing samples from a probability distribution while enforcing constraints that exclude certain values. What does this mean? So basically what I'm trying to do, as I mentioned before, is that I'm trying to, from a large distribution, I'm trying to sample in such a manner that that the new distribution that I sample from is representative of of the true distribution. So I know for a fact that my true distribution is different from what I estimate. So how about I sample in a manner that the estimated distribution now looks closer to the true distribution. That is the basic idea of of sampling, like truncation sampling. And the word truncation means that I truncate at some point, that after some point I actually don't consider uh, certain tokens. So examples of sampling include rejection sampling that we'll discuss, transformation methods, even MCMCs, so Markov change Monte Carlos used in RF. And in context of decoding strategies for LLMs, truncation sampling actually helps in three measures. One is that it obviously prevents rare and unlikely words. So because, as I mentioned, there is a long tail when you estimate probabilities. So you don't want to sample from the long tail, because all of the long tail basically consists of rare or unlikely words. So it truncates at a point that it does not include any of the rare unlikely words. Second is it balanced determinism and diversity. So basically, the I have this option to like the amount of like the point where I truncate from gives me the liberty to either be more deterministic in my outputs or be more creative or exploratory in my outputs. So I have this movable knob in my decoding that I can make the model have the same tokens, spit out the same tokens, or I can have it more creative tokens going deep into the distribution. So it gives me this flexibility, and it also obviously reduces computation overhead, because I cannot do ancestral sampling and sample across all the 40,000 tokens. That will first be incorrect, because obviously I'm estimating, and second, it will be too computationally expensive, because I have to take a softmax now across all the 40,000 uh 40,000 tokens at every step. So that's actually again a bottleneck. So in essence, what sampling tries to solve, some might have noticed while I'm saying it, is it solves this very classical exploration exploitation problem while decoding tokens in LLMs. So let's actually, so this is what the paper, so this was all known before this paper. The background, obviously the paper did mention, like they mentioned it, but obviously it was known beforehand as well. So now this is what where the paper comes into the picture. So the first question that the paper asks is, why is truncation sampling effective? Now we know empirically that it is effective when compared to other methods, like greedy decoding. I just take the first token, or I take ancestral sampling, such that it generates actually more creative yet coherent responses. But why does it work? So apparently no one actually tried to prove this theoretically before this work. So what what these authors actually go is, they actually reverse engineer what happens when when you perform truncation sampling, and based on the results that you get, you're trying to you're trying to re-engineer the entire process to get those theorems. So retrospectively, when we think about truncation sampling, for some threshold tau, we have some sample tokens given probability pi hat, such that pi hat is greater than tau, with the view that they have non-zero probability. So what this is trying to say is that when we do truncation sampling, that we assume that a token, an estimated token, so whenever in these slides, whenever I have a hat, that is an estimated token, and whenever I have a star, that is the true token distribution, like true token probability. So whenever a token has some estimated probability greater than a threshold tau, then we assume that this token must be in the true support. And when I say in the true support, this means that this token must have a non-zero probability of occurring at that prefix. So its pi star is greater than zero. So this is our basic assumption. So just trying to work with these equations, what we get is pi hat is less than pi star plus some tau for every token I. So mathematically, what this means is, whenever we are trying to like our overestimation of any probability is additively upper bounded. So just to come back to what is an overestimation here, an overestimation here is, for example, if let's say assume this first blue arrow, if a particular token had a true probability of 0. Let's say 2, but I estimated its probability as 0.3, then the amount of difference I have is actually additively upper bounded, and this is given by some threshold tau. So this is what comes out of truncation sampling. So how do we prove this theoretically? Now this is a result, so we need to prove if this is what truncation sampling does, but we have to go it inductively. So let's do it from first principle. So okay, so let's start by bounding the log probability using first principles. So what is the idea? The idea is to bound the difference between a minus a dash, and this is it can either be an underestimation when a is greater than a dash, or an overestimation when a is less than a dash. So we want to get the lower and upper bounds for these two situations. So for underestimation, if I want to take a lower bound, it is fairly trivial that, let's say, if my a and a dash are equal, then uh, then it is zero. So my underestimation can at best be like a true estimation, and it can be lower bounded by zero. And if I want to upper bound it, then I use a simple trick from algebra that says that if max of a minus b uh, is a quantity, then it is always less than max of a minus max of b. And I can also clearly see that max of a can be upper bounded to 0, because if we go again, we find that what my a was is basically just my log of my true token probabilities, I given j. So the maximum that p star ij can be for every token can be 1, and hence the maximum that a can be will be 0. So a actually goes from negative infinity to 0. So this gives us this quantity that the underestimation is actually additively upper bounded by negative min a dash. And here, even if though it might look counterintuitive, a dash is actually negative, so hence this is a positive number. So my underestimation is negative bounded by some positive number, and we consider that delta here. So using this result, how do we show overestimation? So here we have shown underestimation is upper bounded, and the authors actually show that using this result, you can show that the overestimation can be lower bounded by some tau. So what this means is, uh, let's say if I have a minus a hat, or a minus a dash is less than equal to some delta, and here the delta is negative min of a dash, then I can also alternatively show it as pi hat is greater than equal to pi star into exponent of negative delta. This is, I'm just like, if you look closely, I'm just substituting the terms here. I'm just taking out the log and putting it to an exponent. And then the authors actually show that this can lead to a result where I show that the overestimation can be lower bounded. So this is the proof that they show. It is fairly simple. What they do is, let's quickly run over the proof. So what they do is, given the precondition that log pi star minus log pi hat is less than equal to delta for all I, then obviously this is a simple substitution result, like a simple result. And then uh, I can rewrite pi hat minus pi star is using this property that uh, my pi hat is equal to 1 minus summation of all the probabilities other than the token I. So this is what they do is 1 minus the property. So here these terms switch. If you might see, the pi hat minus pi star becomes p star k minus p hat k. And then I actually use some bounding property. So here I use the bounding property here to substitute out p star k, and then I resubstitute the true token probability. And given that this quantity can be at max 1, so my upper boundedness here is 1 minus exponent of negative delta. I would recommend anyone to go through the appendix to check out this proof, but it's a fairly simple proof that I can see that. And this actually looks very similar to what truncation sampling is. So here we have proven inductively that the difference, like my overestimation, like my pi dash minus pi star, is actually additively upper bounded to some is actually upper bounded by some numeric quantity, and this quantity is definitely greater or equal to 1 minus exponent of negative delta. How do we connect the dots? Now there was a lot of math here. If you want, you can like go back and listen to it, or you can also obviously read the paper. It is much more elaborate, but the idea what they're trying to say here is that if given tau greater than 1 minus exponent of minus delta, so if for any tau which is greater than this particular quantity in truncation sampling, then what am I doing? So if my uh, if my token distribution, so uh, if my true token is actually not, it shouldn't be sampled. If its true probability is 0, then its p hat I will always be less than tau, because we see from here that if my p star is 0, then the estimated probability will always be under some upper bounded by some tau, which is actually greater than 1 minus whatever the number is. So this will mean that I always reject tokens which are not in the true support, using just this estimation tau. And similarly, in a similar sense, if I have anything which is greater than tau, if I have a p hat I which is greater than tau, this means that there there must be a true, like the true token distribution must be non-zero if it has to satisfy this particular condition given by truncation sampling. So this means that using this fixed threshold tau, I'm able to figure out which tokens are in the true distribution and which are not in the true distribution. So these are the two corollaries that the paper presents, and this is what they actually mean when we try to interpret them. So this was a theoretical explanation of truncation sampling. Just to brief, what we did was we basically went through how truncation sampling, what is it, then what does it actually imply, and then how do we prove that it works. And this is how we came up, how we actually sample from the true tokens and discard whichever are not in the true support. So let's come to the main part of the paper, which is basis aware sampling. So after proving the theoretical explanation of truncation sampling, let's go through some of their drawbacks. So now this all looks very nice, that okay, truncation sampling actually helps you figure out which tokens are in the true support or not. But then what are the problems? Obviously, still there is a lot of research that goes across trying to improve on decoding strategies. So obviously this is not a solved problem. And just to know why this is not a solved problem, so truncation sampling is monotonic. That is, if a model assigns more probability to a bad token than a good token, then there is no threshold that discards the bad token without discarding the good token. Now what does this mean? That in order for truncation sampling to be effective, we have to make sure that the relative order of my estimated probabilities to my true probabilities is the same. So for example, in if my true probabilities gives me uh, such that the probability of A is greater than B is greater than C is greater than D is greater than E, then if I mess up this order when I'm estimating it, there is no way that I can sample a correct probability without that I can sample a good word without including like a bad word, or like without including a word which is not in the true support. So I've just given an example that, say these are my true probabilities in green. Then here there is a rare word which I do not want to sample, and there is this word maybe which I want to sample. But if this is what I estimate, then there is no way I can include maybe without including rare word. And if I do not include rare word, then I cannot include maybe ever. So this is like the problem of truncation sampling, that it is monotonic in nature. So I have to make sure that someone has to make sure that the order of tokens are always same, even if the relative, like the absolute difference might change, but the order of their occurrence remains same in estimation, while in as it is in true probabilities. So how do we solve this? This might actually sound very naive, that okay, this is something that you obviously cannot solve. Like, how do you, if I already knew what the order is, then I would have used that order in my estimation, right? So this sounds like a very chicken and egg problem to solve, but they actually somehow do it. So let's know how. So insights from the softmax bottleneck. So just coming back to this thing called softmax bottleneck, here is actually a better representation which I could have added earlier, but anyways. So here I have a hidden state. I have my feed forward network which projects my d-dimensional space into a v-dimensional space, and then I have a softmax which gives me my probabilities. Now the paper mentions that this is a v minus one dimensional space. Now I took a lot of time to understand why this is a v minus one dimensional space, but it apparently turns out it's fairly simple. The reason why there is a loss of a dimension here is because when I take a softmax, I reduce the degree of freedom because I have this bound where all the probabilities need to add up to 1 and all the probabilities need to be positive. So because I'm decreasing this free like the amount of freedom, the dimension actually decreases by 1. So this at the end is a v minus 1 dimensional space. For simplicity, let's just consider it's a v dimensional space. Then what is happening is I'm trying to estimate from all the probabilities. I'm only able to estimate this particular p dash, which is in this space, which is a subset of all probabilities. Because as we know, whenever we do low rank approximation over a high dimensional space, we have an illusion of covering the whole space, but we actually only cover a sub part of the space. So this is what's happening, that I'm only able to cover the darker gray area, while all of my true probabilities lie in, let's say, this lighter gray area. And my like my actual true probability for, let's say, a particular prefix is some point, and let's assume that this point is not in a reachable space. So let's assume this point is outside the dark gray area. Then what I'm trying to show is the minimum cross entropy loss is actually the one that is closest to what I can reach. So what my model tries to do is it tries to go as close as possible to the true distribution, to the point it can go, basically to the amount of availability, like to the amount of expressiveness it has in its in the model. It basically tries to go as close as possible uh, to the true distribution. Now some might actually relate this to the approximation error that we see in machine learning problems, that we have this classical thing that, okay, machine learning problems have three types of errors. One is an approximation error, one is an estimation error, and one is simple like optimization error. So this is actually very similar to approximation error, which I might be wrong, but this is what I think it is. It is very similar to approximation error, where I cannot actually go through the entire space, so I just go as close as possible to the real distribution. So what does basis aware sampling actually get from? So this is like this can be inferred from the softmax bottleneck. So what does they infer? That they say that if p hat is the predicted distribution from a cross entropy minimizing model, it is basically a fit, like a properly fit model with embedding matrix w, and if there is no valid probability distribution p such that pi, or the probability for ith token is 0, and w, like basically this particular equation, so this basically means that the model is well fit. They basically show that if this equation is true, then the model is considered to be well fit. I mean, the model is properly trained. Then the token's true probability pi star is greater than 0. So how did they come up with this? So it's very simple. Like if we think about it, what they're trying to say is that from all the possible best solutions, I have that all the possible solutions where I have minimum cross entropy loss, if there are no solutions where for a particular token the probability is 0, then this means that the probability of the token, like the true probability of the token, must be non-zero. Now we can prove actually this by contradiction, which I have done here. Or in other words, the token must have been in the true distribution, because the model could never avoid assigning it non-zero mass without hurting performance. So let's say if the model actually assigned it pi is equal to 0, then this means that it is not in our valid solutions, and this means that there must be some example where this token is actually used, where this particular token is used after a prefix. So assuming that this token is used after a prefix, it will always lie in a really fit solution. Now this is actually a difficult thing to understand. I found it very difficult to understand, so I would actually recommend readers to actually go through that section of the paper. They do a reasonably good job in explaining how it works. But if if you want to come back to knowing why this works, I think a counter intuitive example, like a counter argument, might be better, that there can be no way that this token had zero probability, because if it had, then then the solution will not be then the model won't have minimum cross entropy loss. So that is how I think about it. So this is like this is the second theorem that they give, that if a token if there is no model that has pi is equal to 0, basically for a token probability is equal to 0, then the true probability is 0. So now I have two of these theorems. One is the second corollary from their paper, where pi star is greater than 0 if it is greater than some threshold. That is one. And second is if it is if there is no pi is equal to 0 in all of my correct solutions, let's say, if I want to be loosely termed. So this gives us to the new sampling technique that they introduce. So what they're trying to introduce here is, if a linear optimizer determines that there does not exist a feasible solution p such that pi is equal to 0, and such that the probability of like the estimated token here, actually it should be pi hat, but pi hat is equal to 0 among all the rejected tokens for a truly fit model, then its true probability should be greater than 0. So what I'm trying to do is, I'll actually, so this is it's harder to understand from an equation. So what I did is I gave an example what this sampling, how this sampling works. Excuse me. So how do we go about this? First, we use a simple threshold sampling method to sample the most likely tokens. So for example, let's say I use eta sampling in our case, and I just sample the most likely token. So here my red line corresponds to where I put my threshold. So I just sample un as my tokens, and I, for now, I discard the other tokens for like in as the first step. Then second, what I do is I use the basis aware rejection sampling technique on all the discarded tokens to sample tokens who have non-zero support. So out of the tokens that I actually discarded, which is rare word, maybe, and two, I use the like assumption that for all of my correctly obtained solutions, if none of the solutions have the have this term where p of rare word is 0, or p of maybe is 0, or p of 2 is 0, then I actually sample that token. So in my case, let's say for rare word and 2, there are certain solutions where the estimated like the estimated token, like the estimated probability is 0, but for maybe, let's say, the estimated probability is greater than 0. Then this means that maybe has occurred somewhere in my training sample, and hence it should have a non-zero true probability. So I actually sample maybe. So this is called rejection sampling, that I have a pair of rejected samples, like I have a distribution of reject samples, and then I actually post hoc accept some samples based on some conditions. So this is a one of the rejection sampling techniques. So this is how they want to build upon the current technique of threshold sampling. So now that we have understood what new technique they have introduced here, let's go through some experiments and to see if it actually works. So first is obviously qualitative results. So what I showed here from a simple example, they showed using multiple examples. So here, if you see, there are certain lines which show where I have put a threshold on, and ideally in my case, in let's say if I just had truncation sampling, all of this will be rejected, all of this won't be sampled. But now I actually sample these three other tokens based on my basis aware resampling. So this happens across a lot of examples, and they show how some of these examples, like some of these sample methods, actually make sense here. So if you want to look into it, you can look into it. So Donald Grover is like a reasonable, probably a reasonable name, etc. So yeah, this is some of the qualitative results. Now coming to quantitative results. Now they actually, in my opinion, they are mixed results. I as a reviewer, I won't be very sure about a lot of some of their evaluations, but to basically summarize, they had three form of evaluations. One is they actually checked whether model size affected performance. So as their baseline, they used two simple techniques called eta sampling and epsilon sampling, which are two truncation sampling methods, and also nucleus sampling. And then for their new methods, they used a basis aware eta and a basis aware epsilon methods to show how the MAUE, the MOV score, increases. So a MOV is basically just a measure on how similar the distribution of text generated by a model is to a human text. It basically tries to it's a very nice paper, and it has a very extensive documentation which I've linked here. It's actually, I think, one of the new outstanding paper awards. So it basically compares whether the distribution of text generated by a model can be compared to human text. So the higher the mouse score, the better it is. So in simple terms, so they show that across model size, the BAN more or less performs similar or sometimes better than the regular truncation method. Now the results are actually mixed, so they do not make a big claim about it. But here in the second, in the blue box, they show that effect of low eta. So uh, basically low eta is, if I want to recall, eta was basically my threshold heuristic, right? So if I have a low eta, that means that I'm going closer towards greedy decoding. I'm trying to um, have less exploration and more determinism. So whenever I have lower eta, uh, at that time my BA sampling outperforms eta sampling. Now this is actually very intuitive, because what happens is my BA sampling actually samples after my eta. So now it has more options to sample more, let's say, important words that the threshold sampling missed out on. So the closer my, like smaller my threshold line is here on the left hand side, the more chance I have to actually sample tokens which are which have non-zero true probability. So this is a very logical uh, intuition, and actually by results also they show that the mouse score, like it basically reduces faster for eta than for BA eta. This means that BA eta is actually effective. And for human evaluation, obviously they perform, like they do some experimentation, and they show that it narrowly prefers B eta over eta. But I think obviously human evaluation should, in my opinion, should not be a big like concern here, because uh, for any human it is, these are very subjective calls to take, whether this particular, whether this very niche method actually helped trying to sample from true distribution. It, like a rather statistical method, will be, I think, more helpful to know. Yeah, I'm not very concerned about the. So this brings us to the last part, which is discussion and conclusion. So what are the key takeaways from this work? One is that under low entropy generation, that we saw in just in the last slide, that BAT offers clear advantages to threshold sampling, where only a few tokens are permissible. Now, this is very intuitive, because say my truncation is actually very small, that I truncate after only a few tokens. So now I have a bigger pool where of tokens to actually positively sample from, like I take the tokens out. So it is a higher chance that some of the tokens that I truncated out, that I did not consider, have a true probability is greater than zero. So if this of these lines actually go left, that means that I take less number of tokens, then there is a good chance that the true tokens that I actually want to sample will be sampled by BAT, which threshold naively just rejects. So very logical conclusion that for low entropy generation, BAT offers clear advantages. However, this does not mean that BAT is beneficial when we compare to some different strategies like nucleus. So as in the second point, I see that BAT nucleus actually performs significantly worse than nucleus sampling. Now the authors actually posit, they hypothesize that this is because the underlying assumption that I take a threshold on individual tokens is not true for nucleus. So for all the other strategies like eta sampling or epsilon sampling or top k, what happens is you put a threshold at individual tokens if they have a probability greater than some threshold. But in case of nucleus sampling, if we recall, we actually take the sum of certain tokens, and once the sum reaches a certain threshold, then we put a truncation at that point. So the assumptions are actually slightly different in case of nucleus sampling, and hence BAT nucleus does not follow the smooth properties that the paper presents for other while using other properties, while using other sampling techniques. And the third point is that in some scenarios where so in some scenarios, BA eta, basically basis aware, actually accepts no tokens. So sometimes what happens is, let's say if my in the case that in the case where my token distribution actually does not look, my estimation actually does not look very good, in that sense sometimes I generate an end of sentence token, or I just generate, like, I do not really sample from a lot of tokens. I revert back to a greedy decoding in truncation sampling. But something like this cannot be automatically known, because it works on rejection sampling. So it has to sample something out, and this will likely be tokens which do not have true zero probability. So it's an intricate issue that the authors mentioned. But I think, in my opinion, these are the discussions that the authors mentioned. But I think, in my opinion, the computational requirement is actually something that needs to be considered more. and also the extensibility. So one is that how computationally efficient is BAT. The authors mentioned that now that you only have to sample from the rejected tokens of the truncation sampling, so it is still not as big of a computational concern. But then the performance is actually better when the truncation sampling is limited in effectiveness. So this is like a counter argument to the advantage that BAT offered. So something needs to be looked upon. And otherwise, I think uh, nucleus sampling does work empirically the best in most of the, like, in most examples, most scores. So given that BAT nucleus does not outperform nucleus, so this won't be a very good extension, because most of the models assume that by default we presume nucleus sampling. So that will be one key concern in implementing this uh, in future research. And otherwise, I think there is this nice so obviously this paper was submitted and accepted at ICLR as a poster. So there are a lot of there are three very good reviews on open reviews. I would suggest if anyone wants to have a look at it for future directions. But yeah, that was about it. Thank you for listening. uh, if you want to listen to more of such presentations, you can go to this link, which is basically my portfolio website. This is the first time I'm doing such things, so this is might be the only blog currently, like the only explanation currently. But I plan to add some more given time, given I have enough time. But yeah, thank you.